Namaskar and welcome back to another lecture in our series Development and Applications of Special Concretes under this program of Massive Open Online Courses initiative of the Government of India. We continue our discussion today on self-compacting concrete. Today the discussion will focus on proportioning of a self-compacting concrete mix. This will be the last lecture as far as self-compacting concrete is concerned, and possibly the close of this module, which has largely concentrated on self-compacting concrete. The idea in this module has not been to create an expert out of you as far as self-compacting concrete is concerned, but to make you aware of the issues involved, the basic approach that is used, the history that went into the creation of self-compacting concrete, the testing of this special concrete in terms of the different tests that we use, and the nuances involved. What are the details? How exactly the test is to be carried out? Please remember that a knowledge of merely how the test is carried out does not make you an expert. You have to have the right kind of specifications. For example, if you're carrying out the slump flow test, you should know what to look for, what small details are required. For example, from the slump flow, you can make a judgment about segregation resistance, from the V funnel, from the U box, from the L box, and so on. So we have to be careful when we choose one test or the other in specifying a self-compacting concrete. To reiterate once again, today's discussion is on the proportioning of this special concrete mix. Now, this is an old slide from the proportioning that we carried out for normal concretes as a part of the review of your understanding or our understanding of normal concretes. We can see that coarse aggregate constitutes about 40% of the entire concrete mix by volume. Fine aggregate is another 22%. Mineral admixture is about 48 liters. Cement is about 100 liters and water is about 180 liters. That's about 18%. Cement and mineral admixtures constitute about 150 liters. That's about 15% of the concrete by volume, air being taken as 5%. By weight, this proportion translates to what is given here. And let me recollect what we did very simply to get these numbers. We said that we will have a workability versus water content relation known to us. And if the workability increases for a given workability, we'll first get the water content. And we had a similar discussion for strength versus water cement ratio. This relationship was known to us for a given strength. We know the water cement ratio, and therefore, knowing the water content from here, we know the cement content. We calculate the cement content by mass, convert that to volume using the specific gravity of cement, and then we were using this picture all the time that we knew how much of the air is there, then we said water, then we said cement, and this space that we had left here, we divided using the concept of S by A. So this was the purely mechanical arithmetic kind of an exercise that we did. The principles behind it we had revised, and it turned out that this was one of the approaches that we can use to proportion a concrete mix using primarily a volumetric balance using this 1000-liter pitcher. So we use the story of the crow to say that as far as the pitcher is concerned, the solid volume, the absolute volume of all the constituents must total to 1000 liters or a cubic meter. Now that principle is pretty much inviolate, and we have to stick to that principle as far as self-compacting concretes is concerned, except that we may not be able to stick to this algorithm, and that's what we will see as we go along in our discussion today. As far as the characteristics of proportioning self-compacting concretes is concerned, cement-based paste content in self-compacting concretes is high due to the need to keep good workability in low water to powder ratios. So we need to keep low water to powder ratios. That is, the powder content has to be high, the water content has to be low. Moving forward, the powder content needs to be increased and the water content is restrained or should be kept at an adequately low level. Mineral admixtures are used to increase the powder content, which increases the paste content, and if that happens, it leads to a decreased volume of coarse aggregates and ensures the required viscosity of the paste at the low water to powder ratios. So if we increase the powder content, the viscosity or the segregation resistance of that paste increases. High workability is also achieved through using high performance superplasticizers, and we get cohesiveness from using the viscosity modifying agents. We've possibly talked about this earlier, that as far as self-compacting concretes are concerned, we have two important routes. One is increased powder content and the other is using cohesive mixes or a cohesive modifier, that is your viscosity modifiers. So these are the two routes that we can take, a combination of these two things that we do to normal concretes to get self-compacting concrete. From a rheological point of view, fresh self-compacting concrete should have a low yield stress and moderate viscosity. Two major categories therefore emerge: powder type SCC and VMA type SCC. So powder type SCC means primarily we are trying to push the powder content. VMA type means that primarily we are trying to impart the viscosity through viscosity modifiers. Now let us review some basic features of the powder type self-compacting concrete mixes. This is developed from the normal concretes through the use of modified mixed proportions, and for a given volume of concrete, what we try to achieve is we limit the volume of coarse aggregates. That is, the volume of coarse aggregates in self-compacting concretes is less than that in normal concrete. The volume of sand in self-compacting concrete is higher than the conventional concrete, and this contributes to the mortar content. So the mortar content in self-compacting concrete is higher. Cementitious material content is also higher than in normal concrete. When we talk of cementitious material, we are talking of cement and mineral admixtures. But please remember that apart from mineral admixtures, we also sometimes use other powders which do not necessarily take part in the hydration reaction. So if they take part in hydration reaction, they become part of the mineral admixture. If they do not take part in the hydration reaction, they can still be part of the paste because they are comparable in fineness to normal cements or mineral admixtures and contribute to the higher powder content. And what we are actually interested to do is to increase the powder content. Please remember that the cementitious material content, the terminology is very useful when we are talking in terms of strength. But when we are talking of the water to the powder ratio, then we are really interested not so much in strength, but the segregation resistance or viscosity or the kind of properties of the paste in the fresh state. So continuing further, the water content in self-compacting concrete and normal concrete mixes is more or less similar. What we should keep in mind is that from the historical perspective, self-compacting concretes were developed largely from normal concretes, and therefore the effort was that in self-compacting concrete, to the extent possible, we should not try to tamper the procedures, the material specifications and so on, which are already known to engineers by way of normal concrete. Thus, in self-compacting concrete, a relatively low water to cement ratio, more specifically a lower water to cementitious material ratio, and actually more specifically we can talk in terms of a low water to powder ratio is achieved. Continuing with our discussion on powder type self-compacting concretes, low aggregate content is essential to achieve the high deformability and flow speed as they reduce the frequency of collision and solid to solid friction. So basically we are trying to control or restrict the amount of coarse aggregate. We try to restrict this coarse aggregate content to a low value. Now, how much is that low value is something what we will see in the subsequent slides. We go for a higher sand to total aggregate ratio in self-compacting concrete to maintain the moderate levels of viscosity. Now, this higher sand to total aggregate ratio essentially refers to the good old parameter S by A, except that we often do not approach it from the direction of S by A, but that is what it will boil down to. Given the fact that we are familiar with the concept of S by A, which is the parameter which we use to divide this space of inert material that we have in the pitcher of 1000 liters into sand and coarse aggregate, I have included this approach or this sentence here just to put the discussion that we have in perspective. The increase in the paste volume of self-compacting concrete mixtures is achieved by the increase in the powder content. That's what we talked about just now. We said that, okay, there is a water-cement ratio, there is a water to cementitious material ratio, and there is a water to powder ratio. They are not the same thing as far as self-compacting concretes is concerned. I've already explained to you that water-cement ratio and water-cementitious material ratio really refers to the contribution or understanding from the point of view of strength, whereas water to powder ratio is more important from the point of view of workability or the viscosity of the concrete that we are talking about. And of course, what's written here is with a lower water to binder ratio. The word binder here refers to cementitious materials. The powders utilized in the powder type SCC include silica fume, fly ash, ground limestone fines with different size distributions. Of course, we should also remember that the sand, that is fine aggregate, also has a certain amount of fines. And as far as self-compacting concretes are concerned, as we shall see later, the fines from here also are considered as part of the paste, as we will see in subsequent slides. Now coming to the second class of the self-compacting concretes, that is the viscosity modifying type, SCC, superplasticizers and viscosity modifiers are added to the mix to meet the rheological requirements. The rheological requirements is in terms of the workability and so on, and then parameters that define the rheology with which the engineers are not necessarily very conversant with at times. Adding superplasticizers helps in reducing the yield stress of the self-compacting concrete with limited influence of viscosity. Incorporating the VMA improves the cohesiveness of the mix. VMA are usually water-soluble polymers and adsorbent cement particles, and they provide adhesion to the aggregate. One of the examples of VMA is the Vellanka. In these concretes, the required workability, if controlled by superplasticizer dosage and the required segregation stability, that is viscosity, is obtained by a particular dosage or an appropriate dosage of the viscosity modifying agents. Now let's try to do an illustrative example of a concrete mix proportioning for SCC based on IS 10262. These are the conditions that are known to us. We want an M30 grade concrete. We know that we'll use OPC 43 grade cement. The nominal maximum size of aggregate is 20 mm. The exposure conditions is severe for reinforced concrete. And the characteristics that we give is slump flow class is SF3. The passing ability using an L-box test H2 by H1 is known to be 0.9. The V funnel flow time is in the class of V1, and segregation resistance is in the class of SR1. As far as these terms or requirements are concerned, we've covered this discussion when we talked about testing of self-compacting concrete mixes, and you can go back and see what are the kind of values that we are looking for. But what it also draws your attention to is that as far as the properties of self-compacting concrete in the fresh state is concerned, it is not only the air content and so on, or workability given just in terms of slump, but there is a lot of tests which are given to you that all these criteria need to be satisfied. The degree of site control is good, the type of aggregate is crushed and angular, the maximum cement content is required to be limited to 450 kgs per cubic meter, A normal superplasticizer of the polycarboxylate ether is available to you, and we are expected to use fly ash. Now this information is known to us as we start proportioning the self-compacting concrete mix. The details of the material available are here. Specific gravity of cement, fly ash, coarse aggregate, sand, chemical admixture, all these are known to you, 3.15, 2.2, 2.7, 2.65 and so on. Water absorption for coarse aggregate and sand is known to you. We say that okay, there will be no surface water on coarse aggregate and sand. Sieve analysis is known to you from coarse aggregate. It conforms to table 7 of IS 383, and sand conforms to zone 2 of table 9 of IS 383, and also the information about the material finer than 0.125 mm is known to you from sand, and that is given to be 8%. So what I said in one of the slides just now was that as far as the fines are concerned in self-compacting concrete, they come not only from cement and related things, which is the mineral admixtures, any kind of other powder that you may use, but also from the part of sand, depending on how much is the fines present in the sand. I would also like to remind you that when we give the properties of fresh concrete, like was given in the previous slide in terms of the V-funnel test or the L-box test or the slump flow and so on, then all these tests have to be carried out in the fresh state, and somebody has to determine and verify that all these criteria are met. If one of these criteria are not met, then we have to go back to the drawing board, make a modification in the mix, and try to evolve or try to develop a mix where all these criteria are satisfied. So the first step, we know that as far as the strength is concerned, we try to get this target strength of the mix using the characteristic strength. We know in this case we are working with M30 using this factor of 1.65 times S or a factor which is FCK plus X, whichever is higher. So in this case, from the tables which are already known to you, S is supposed known to be 5 and X is supposed to be 6.5. We take F target, that is the target mean strength of the concrete that we are trying to proportion, as 30 plus maximum of these two numbers, which turns out to be 38.25. I'm sure you would remember this part of our exercise where we are trying to determine the mean strength of the concrete, and this mean strength will help us ensure that only 5% of the specimens fall below this number. And as you can see here, this mean strength is from here because 5% failure is allowed. 1.65 is the factor that you will get, and S is the standard deviation that we get from the site conditions. And apart from this, a certain fixed number is also given to you. So obviously, if you are able to reduce your standard deviation to, let's say, 1 or 2, then this number will become very small. What the code is telling you is that in those cases, the proportioning cannot be too close to M30, but it should be at least 6.5 MPa away from this characteristic value. So you are allowed to, or you are encouraged to bring your standard deviations in a certain range, but you should be targeting a mean strength at least 6.5 MPa above the characteristic strength. Please go back to the drawing board and check these provisions for normal concretes and see if they are any different from this provision in self-compacting concretes. Then we go back to try to figure out the approximate air content that we want to assume, and as per table 3 of 10262, the approximate air entrapped in a 20 mm size aggregate is 1%. So we know that 10 liters out of the 1000 liters will be gone as far as air is concerned. Then the next step here is to find out the water cementitious material ratio. So see, we are not trying to determine the water first, we are trying to determine the water cementitious material ratio. And if some data or some guideline is available to us for a given strength, how much is the water cement ratio or the water cementitious material ratio that we need, then it's a very straightforward exercise. If we do that for 38.25, which was our target mean strength, we find that the water cementitious material ratio is 0.43. And we can always check this value with respect to any prescription that we may have in IS 456 or any other document for a given exposure condition. So for example, in this case, we were told or we knew that the reinforced concrete that we are proportioning or the concrete we are proportioning is for a reinforced concrete structure in severe environment where the water cement ratio should not exceed 0.45, and since we are getting 0.43, it is okay. We assume the water to be 195 kgs a cubic meter. Now the typical range that is given for us as far as IS 10262 is concerned is 150 to 210. We begin with 195 based on past experience. Now you will realize that a lot of mixed proportioning exercise has past experience and given values. Now that is something which is typical of concrete mixes where a lot of discussion is largely empirical. So we cannot just help it. We have to start with something, then modify very quickly, and we'll converge. That becomes part of our experience, that part becomes part of our past knowledge. Now once we use this 195, we get 453 as the corresponding, not the cement content really, but the cementitious material content, using this water cementitious material or water binder ratio to be 0.43. Now this is what we would like to determine or bifurcate to ordinary Portland cement or fly ash. The usual fly ash content is about 25 to 50% for self-compacting concretes. So in this case, let's take fly ash to be 40%. Now this 40% means that 0.4 of this, which is 182 kgs, will go to fly ash, and the remaining 60%, that's 271 kgs, will become OPC. Now once we are doing this, we are not using the concept of efficiency of fly ash. So we are assuming that all of it will contribute to the hydration process and strength, but that's something a matter of convention. That's something which we just keep at the back of our mind, and we need to carry out experiments to determine what kind of strength values you get. So I'm not getting into that discussion here once again, but just a flag for you to be careful. Now coming to the selection of chemical admixture content. So let the dosage be 0.6% by mass of cementitious materials. That's something which has to be prescribed and told to us by the manufacturer, and we need to verify it at site using the material that we are actually going to use as far as the construction is concerned. So therefore the quantity of the PCE plasticizer will be 0.6% of 453, which is 271 or 2.71 kgs a cubic meter. So once we have this value, we go to powder content. Now this is something which is a very unique step as far as the proportioning of self-compacting concretes is concerned, because water to powder ratio is an important player in the whole game, other than simply the water cement ratio or the water cementitious material ratio that we always talked about from the strength perspective. Now the powder content here corresponds to all fines less than 0.125 mm. This is a matter of convention, and we say that so long as the powder that is being used is less than 0.125, it will all contribute towards the paste content as far as that concrete is concerned. So now OPC, fly ash, and the sand component finer than 0.125 will all be a part of powder. Now the selection of the powder content is based on the class of the segregation resistance and viscosity which is required. So how much powder do we need in a particular self-compacting concrete is determined by how much of segregation resistance or what is the V funnel time that we want from the concrete. And since in this case it is given to us to be SR1 and V1, the mix should be adequately cohesive, we take the powder content to be 520 kgs per cubic meter, which is almost the middle of this typical range of 400 to 600 kgs a cubic meter. So we fix the powder content to be 520, or we take the powder content to be 520 and try to find out, now how do we achieve this 520? Out of the 520, we know that the fines that required to be contributed by the fine aggregate will be 520 minus the fines that are already there. All the fly ash which is there is fines, all the cement which is there is fines. Therefore, it is 182 plus 271, which we've already done, gives us 67 kgs of fines have to be contributed by fine aggregate, that is sand. Now the sieve analysis, the information that we have about the sieve analysis tells us that the sand has only 8% fines. Now in order to get 67 kgs of fines from a material which has 8% of fines, we need the sand content to be 838 kgs. Now just look at this number and try to compare it mentally with the kind of sand content that we normally encounter as far as concrete is concerned. You will realize that this value is much larger. So having said that, the coarse aggregate content is now getting fixed, because this is nothing but 1 unity minus the air content minus the content of water, cement, fly ash, admixture and fine aggregate. So if we subtract all this from here, 195, that is water, 271 is cement, 182 is fly ash, 271 is my admixture, and 838 is my fine aggregate, that is sand. We find that the volume of coarse aggregate is 0.31 cubic meters, that is 310 liters. Now this 310 liters translates to 849 kgs as far as the mass is concerned. So we are looking at a self-compacting concrete with about 30% or 31% of coarse aggregates. Now let's check the total powder content in the mix. The volume of powder is the volume of OPC plus volume of fly ash plus the volume of fine aggregate, finer than 0.125, and that's something which is known to us. And we find that this number is nothing but 0.194 cubic meters. So the 67 is contributing to this 194, and the volume of powder is 19% as far as the volumetric ratio is concerned. So now the ratio of water to powder by volume is 0.195 by 0.194. 0.195 is 195 kgs per cubic meter of water that we started with, and 194 is what we got here, and that is how we can calculate the water powder volume ratio. And it's acceptable to us because the normal range recommended as far as the water powder ratio is concerned is 0.85 to 1.1. Basically we are targeting equal volumes of water and the total fines. So the mean value is 1. It could vary by about 10 to 15% either way, and this is a very specific check once again as far as self-compacting concrete is concerned. So now we'll move on to determination of the coarse aggregate in the next step. Having done this exercise, this is our final trial one for the mixed proportion for this SCC, the self-compacting concrete. 195 kgs of water, 271 kgs of cement, 182 of fly ash, 838 of fine aggregate and 849 of coarse aggregate with 2.71 kgs of chemical admixture, and the powder content is 520. So the total aggregate content may be proportion between 20 and 10 mm aggregates, because when we talk of coarse aggregates, we are talking of material greater than 4.75 mm. And in India, most of the time we get coarse aggregate in two classes. One is the 10 mm class and the other is the 20 mm class. So how much of 10 mm and how much of 20 mm should be used to give me a value of this 849? That has to be determined again based on sieve analysis and particle size distribution that is there for these two aggregates that we get, and make sure that the overall grading curve satisfies the table 7 of IS 383. So what these tables tell you really, as far as the grading curve is concerned, that if we have the size of aggregates here and let's say percentage finer than somewhere here, how will it look like? Finally, there will be a size here which will correspond to a value 100% is finer than this value. Also, there will be a size here where you will find nothing is finer than this value. So whatever happens here, there is a particular, for every size we need to have a certain value for percentage finer than, and these values are often given to us in a code by way of a distribution. It is known that after all, when we are buying or when we are getting aggregates into site, it is not possible every time to come to a particular value for a particular finer than value. Therefore, we are given a certain range here or a certain range here, whichever way you want to look at it, that okay, so long as particles finer than 10 mm is concerned, they should be at least 50% or 60%, in the range of 40 to 60% or the range of 45 to 55%. So that is how we try to specify this. You can try to go back and read the literature about it, read the codes as to how this overall grading curve is given. So you cannot have a aggregate grading curve of yours which is outside this, which gives you values which are here or here. That is not allowed. So you need to proportion or mix your 10 mm and 20 mm aggregates to make sure that your overall aggregate fits into this range that has been given in IS 383 or any such similar document. Of course, then we need to go to the trial tests, trial batches, and final mix design, which could be based on the slump flow, L-box, segregation resistance. V-funnel tests need to be carried out to ensure that the mix meets the necessary flow and viscosity requirements. If satisfactory performance is not obtained, the mix of course should be redesigned. And based on these trials, there could be a need to add VMA to improve the cohesiveness of the mix. So what we have shown here is the powder type approach to self-compacting concretes, where we said that the minimum powder content should be such and such, and we did not use VMA. If we need to use VMA, of course, VMA is a admixture which can be used, and that will modify the properties of your paste phase and therefore the mortar phase and therefore the concrete. So with that, we come to a close more or less of the proportioning part. So I'm sure you realize that if a lot of information is given to you, then proportioning is more or less an algebraic exercise which is reasonably straightforward. But what goes on behind that is something which we must also never lose sight of. So these pictures are all known to you, and I've taken them from the previous slides that I've already used. This is concrete being pushed through pipes, and here we have what we had discussed as aggregate interlock. We do not want this to happen. We want the concrete to move smoothly. Now, whether this kind of a profile develops or this kind of a profile develops depends on what happens at the interfaces. That's what is shown here. This shows segregation of aggregate, that is, the mortar component of this concrete could not support these coarse aggregates here, which have settled down. And all this discussion here relates really to a concrete which is something like this, which has been modeled something like this here. So what we are talking about really is this coarse aggregate, its characteristics and its particle size distribution, its individual characteristics in terms of shape, etc., and particle size distribution. How many of these particles are smaller, how many are much smaller, and what is the maximum size of these aggregates, and so on. This understanding we need to have to kind of understand or try to keep at the back of our mind that this whole thing really represents this concrete. In other words, this concrete is being represented through these kind of pictures. And when we are trying to proportion a mix, we are trying to determine the properties of the mortar phase, that is shown here in different ways, and the coarse aggregate phase, which is shown here, and make sure that the concrete doesn't segregate. It has the right kind of viscosity. For that, the mortar has to have the right kind of viscosity, and finally the paste has to have the right kind of viscosity, and they should have the right kind of carrying capacity as far as the coarse aggregate is concerned. So the mortar should have a certain type of characteristics, and that's what we'll see in a few slides before we close our discussion today. This picture we've already seen. This shows you how much of coarse aggregate we have in the system. Of course, all the coarse aggregates have not been really marked in this, but that's more of a image that you must keep in mind. And this is what the particle size distribution of coarse aggregates, let's say, looks like. So we have some very large aggregates, we have smaller than that, maybe smaller than that. This is something in between these two. And what we have here is, this is my void volume. And the way I've shown it here, these aggregates are all in contact with each other. So this is something which is a reiteration from what our very early discussion in this course has been. These aggregates are in contact with each other, which is not really true in concrete. In concrete, the aggregates are not in contact with each other, as we have seen in the previous discussion or the previous slide. So this yellow part, now this yellow part is the minimum amount of mortar that is needed to make this mass into a concrete. Minimum amount of mortar means that amount of mortar which just fills the gap between the aggregates. So the interparticle voids, inter-aggregate voids are now being filled with mortar. So this approach or these kind of concepts are being reiterated several times because they are very important as far as designing or understanding of self-compacting concretes is concerned, because that is the volume of mortar that we have, and then we have to have that characteristics of mortar or the properties of that mortar, and the volume and properties, they have to be judiciously chosen as a combination in order that our concrete meets the right kind of requirements or has the kind of requirements which are acceptable to us. So if we move forward, here is a situation where I have removed the aggregates from the previous picture to one level and another level. So obviously the volume of mortar has gone up, and it has gone up even further in this case. What it means is that as far as the concrete is concerned, for example, in this case, this mortar should have the capability of carrying with it all these aggregates which are shown here. This mortar here should have the properties or ability to carry these many aggregates together with it as it moves through pipes and is trying to be placed as a concrete. So don't you think that the properties of this mortar here, let us call it M1, and the properties of this mortar here, let us call it M2, they need to be different. So as far as the viscosity is concerned, which of them should have a higher viscosity? Mortar M1 needs to have a higher carrying capacity because it is carrying a lot many more aggregates compared to mortar 2, which is carrying fewer aggregates. So this is basically the crux of our discussion. What should be the properties? So if we control the coarse aggregate volume and of course the particle size distribution involved there from the packing perspective, then we can also control, or we can also get a pointer on what kind of material properties we expect as far as the mortar is concerned. So that is what we get involved with when we are talking about the different ratios in terms of the water powder ratio or the total fines content or the total mortar content and so on. So recall that we have provisions relating to the maximum coarse aggregate content depending on the three different types of concrete that we want: normal structures, more congested structures, and so on. So the maximum aggregate content does not exceed 35%. If I remember correctly, please go back and check this number, and that is what is being illustrated here. So I'm not calculating the numbers, I've not calculated how much is the coarse aggregate content here or how much is the coarse aggregate content here. You can always assume that they are spherical particles and carry out this analysis and you will have those numbers. Now this picture here is another representation of the previous one where the properties of this mortar and this mortar have been shown to be different. That's why I've tried to color the mortar differently. So if we have a lesser carrying load, we'll have more mortar with a lesser demand on its carrying capacity. If we have a situation something like this, then we are looking at mortar which is lower in volume but has to have a certain higher demand on the carrying capacity. More or less come to an end of the discussion today, and I'll reiterate that proportioning itself is a reasonably straightforward exercise provided we have all the information and the arithmetic algorithm given to us. If it is not, then it becomes an issue of science. It becomes an issue of carrying out some very simple experiments which are fundamental to the understanding of rheological behavior of concrete, and that's not something which we'll do as part of concrete engineering. We'll do it as part of our special topics discussion, possibly sometime next week. And for this week, we'll close the discussion with only the self-compacting concretes. And I must, as usual, thank all my colleagues, teachers, and friends who have helped me understand the simple concepts of special concretes. This slide gives the suggested reading and references which you might find useful in following the material which has been presented today. However, this list is by no means exhaustive, and in fact it's for that reason that I've written list incomplete, and you are requested and encouraged to look at the internet, look for more relevant material, and try to understand the subject matter better. This slide gives you some ideas as to what you can do. Some of these things we already mentioned in the discussion while you are talking with the different slides, but these kind of things will probably help you understand the concepts better. And with that, I come to an end of the discussion today. Thank you so much for being with us, and I look forward to talking to you once again next week in the next module, when we'll talk of some science related to self-compacting concretes, the proportions, the properties, and then we'll take up a discussion on fiber reinforced concretes. Thank you.